Hello, great friends. I hope you are doing well. IBM is here with another episode of Learning Physics, and this is the last episode of Deformation of Solids. Before I start this, I send greetings to my friends who always leave comments, who always raise complaints. Shahina, I'm very grateful for your complaints and for your suggestions. I'm always trying my level best to work on them to meet your demands. I have been requested to record paper 3 so that students can see how to present their work in paper 3, and I really commit myself to record paper 3 to show some students, and maybe one of the teachers told me is finding challenges with teaching students how to present their work in paper 3. I'll try my level best and give you an example of how I encourage my students to present their work in paper 3. Nevertheless, for today, I want us to accomplish the formation of solids. And let's go to the document. So I think we stopped on page 56, and today I want us to start from page 57. Okay, the first equation. A wire consists of a 3-meter length of metal X joined to a 1-meter length of metal Y. The cross-sectional area of the wire is uniform. So the cross-section area is uniform. A load hung from the wire causes metal X to stretch by 1.5 millimeters and metal Y to stretch by 1.0 millimeters. The same load is then hung from a second wire of the same cross-section area consisting of a 1 meter length of metal X and 3 meters of metal Y. What is the total extension of the second wire? So we have two wires. Both wires are composite wires having X and Y. For the first, X has length 3 meters, Y has 1 meter, but then X stretches by 1.5 and Y stretches by 1.0. For the second wire, X, X has 1 meter and Y has 3 meters. Now we want to find the extension of the second wire. So first of all, note that if I have wire X, even if it is a length 3 meters or length of 1 meter, the Young modulus is the same. So first of all, to begin with, the Young modulus is going to be the same. The Young modulus is the same. And for the same wire, if we are applying the same load and has the same cross-sectional area, it also means the stress is also going to be the same. Since stress is force over area and the cross-sectional area has remained the same load has been added. So stress is going to be the same since F over A is the same. And we know that Young modulus is actually stress divided by strain, which is going to be stress, and strain is extension of original length. So when I get the reciprocal, it becomes original length over extension. So let's begin with metal X. We are going to first of all begin with metal X for the first wire and for the second wire. So if I consider only metal X, let me first look at the first wire. The first wire for metal X, Young modulus, is going to be equal to the stress. It will be stress over strain, but stress is original length is 3 meters, so I'll say 3 times the stress divided by the extension of the first wire. It is 1.5. I will not change the units because I know I'm going to divide quantities, so this will be 1.5 in millimeters. My answer will still remain in millimeters. If I consider the second wire, still for metal X, the second wire, Young modulus, is going to be equal to, because the second wire X has 1 meter, so Young modulus is going to be 1.0 times the stress. Then the extension of this one is not known, so I'll call it EX. But remember, Young modulus is the same, so I can equate these two equations. So it means 3 sigma over 1.5 is going to be equal to 1 sigma divided by EX, which gives us the value of EX. So what is EX? EX is going to be 1.5 divided by 3, which is, I think it is 0.5. So EX is going to be 0.5 millimeters. So EX will extend by 0.5 millimeters. Let's now check on wire metal Y. So here the second wire will extend by 0.5 millimeters. Let's check metal Y. metal Y. For the first wire, the Young modulus is going to be, for metal Y, the original length is 1 meter. So the Young modulus is going to be sigma times 1 meter. There's a 1 there because the length is 1 meter. Divided by the extension of the first wire for metal Y is also 1 millimeter. I will not change the units. Then for the second wire, the Young modulus is going to be equal to the second wire of metal Y. It has length 3 meters, so this will be 3 times the stress divided by the extension that we want to find, EX. Remember, Young modulus is going to be the same, so we shall equate the two equations. So I'll say that sigma over 1 is going to be equal to 3 sigma over EX, which means, EY, not EX, which means that EY is going to be equal to 3 millimeters. So if I want the total extension, because they behave as if they are quantities in series, so total extension is going to be 3 plus 0.5, which is going to give us 3.5 in millimeters. So our answer is going to be B. To determine the mass of food in a pan, a scale is used that has high sensitivity for small masses. That means even if you put a small mass, it stretches so much. However, it has low sensitivity for large masses. Low sensitivity for large masses, it means that now it should also be unable, it should not stretch easily when large masses are put. To do this, two springs are used, each with a different spring constant. One of the springs has a lower spring constant and the other has a high spring constant. Which arrangement of springs would be suitable? Okay, so let's inspect this. Precisely, I will think when I compare this here, this is the spring which does not easily stretch. When I put a mass here, yes, this will stretch, but for smaller masses, because this does not easily stretch, for smaller masses, the sensitivity here will be very low, because this does not easily stretch, and the total extension here is the sum of the extension of these two, but this one does not easily stretch. So it means for smaller masses, the sensitivity here will not be really very good. And let's check here. Of course, this one is automatically out because it is almost the same as the other one. The rigid box is just preventing the spring inside here from overstretching. So this means already it is having a high constant, does not stretch easily. So if I put here small masses, it will not be very sensitive. Even here, when I put these are in parallel, total constant is twice k. Extension becomes even very small, a half of the extension of 1 if they were identical, but note that they are not identical. So the extension is going to be very small, and remember, the extension is going to be dictated by the stiffer spring. Therefore, this one will not also work. That means we remain with only one option, and that is going to be A. Why should it be A? When I add a small mass, the spring of lower k will easily stretch. But when I add a large mass, it will stretch, but the rigid box will prevent it from overstretching. And remember, this one is a stiffer spring. It does not stretch much. So therefore, this will be sensitive to smaller masses because this spring here will stretch. But if I put a large mass, this spring has a limit. The rigid box prevents it from overstretching. And yet the spring at the bottom has a high value of K. It does not easily stretch. So large masses, it will be less sensitive. Therefore, the answer is going to be A. A suspended copper wire is gradually loaded until it stretches just beyond the elastic limit. Just beyond the elastic limit. And it is then gradually unloaded. Which graph, remember it is a copper wire, which graph with arrows indicating the sequence best illustrates the variation of the tensile stress with longitudinal strain. Now note that a copper wire is ductile, it undergoes both elastic and plastic deformation. So here, this is a poor illustration of elastic deformation and plastic deformation because here it is showing, generally this doesn't make sense because look at the graph for loading and for unloading it is going, how can we start with some extension and then we remove the extension? So that means this is not going to make any good sense. Okay. Then we have this one is also not correct. Note that this graph is not starting from the origin, so this one is also not going to be correct. So we remain with these two, but this one is obviously wrong because it is showing that when the material stretches, when the material stretch, actually it is not even a straight line. Yet a copper wire initially obeys Hooke's law up to a certain point. Then when elastic limit is exceeded, then it undergoes plastic deformation, and this is a curve from the origin. So this means this is also out. This is initially a straight line, then somewhere here it undergoes plastic deformation, and when the deforming force is removed, it retains some extension. So the answer is going to be B. What is the ultimate tensile stress? Remember we said ultimate tensile stress is the maximum stress that a material can withstand before it breaks. So the answer is going to be precisely B. A beam, the weight of which may be neglected, is supported by three identical springs, which when a weight W is hung from the middle of the beam, the extension of each spring is X. Okay. Now note that these springs are in parallel, and if they are identical, their total extension is going to be a third of the extension of just one if they are identical. And note that total extension when they are used together with this load is X. So that means X is equal to a third of the extension of just one. So the middle spring and the weight are removed. The middle spring and the weight are removed. What is the extension when a weight of 2W, a weight of twice W, is hung from the middle of the beam? So they have they have now removed the middle spring. They have removed the middle spring, and now the weight W is doubled. So now they have removed that one, and the weight here is twice W. So first of all, these two springs will now extend by a half. In the second case, the total extension is going to be a half of the extension of just one. Initially, remember, the extension of one spring was 3x. So E was 3 times x for one spring. Then, remember here the load was W when they were 3. Now they have told us that the middle spring and the weight are removed. What is the extension when a weight of 2W is hung from the middle of the beam? Now the middle spring has been removed. So the new extension is going to be a half E. Remember we have said E can be 3x. That means the new total extension. But this was 3x when the load was W. This was 3x when the load was W. Now the load has been doubled. The load has been doubled. Okay. So remember by Hooke's law, F is equal to the total constant. Let me just use constant, total constant, K total times total extension, E total. When the load was W, we can establish the total constant. The total constant was, let's just say it was K total. The constant there was K total. Then times the extension, which is times 3x. When the load was W. Now we have two springs. And I'm saying for the two springs, using Hooke's law, F is equal to K total times E total. This time we don't know the total extension, but the load is twice W. But if the springs, if I had only one spring and its extension was this, then the constant, sorry, this was not K total, this was the extension of one spring. If I had only one spring and its extension is 3x, that means if I use K equals to E, it means constant K is going to be W divided by 3E. Now I have the load, so one spring has that. So I have now a load of twice W, and the total constant, because they are in parallel, total constant is going to be 2 times that, because it is going to be, if this has constant K and this one has constant K and they're in parallel, total constant is going to be twice 2K. So this is going to be 2K, then times total extension E total. So total extension, which I'm going to call E total, is going to be equal to 2 has cancelled, so total constant is going to be the weight W divided by the constant K. But remember, the constant K is W over 3E. So when I bring W over 3E here, not 3E, 3X. So E total, not EK, E total is going to be equal to W divided by K, which is W over 3X. So 3X goes up. Why am I writing 3E? 3X goes up and W cancels, so it means total extension here is going to simply be 3X. Therefore, the answer is going to be D. So note, I first of all found total extension, by how much one spring extends. Then using Hooke's law, force is equal to KE. I got the constant of one spring as W over 3X. And now I removed one spring. Using Hooke's law, F is going to be total constant times total extension. Now the load is twice W. But if the springs are in parallel, their total constant is the sum. That's why I have 2K, then times total extension, which I called ET. So I could substitute and find ET as 3X. So the answer is D. Which of the following correctly defines the terms stress, strain, and Young modulus? Stress is force over area. The first column is the same. No. Stress is force over area, so A and B are out. Then strain is extension over original length. Strain is extension over original length. So this one is out. So the answer is automatically going to be C. A wire is stretched by 80 millimeters when a load of 60 newtons is applied. What will be the extension of a wire of the same material, that is the same Young modulus, having 4 times the cross-sectional area and twice the original length? Okay. So we know that Young modulus is equal to force over area times original length over extension. So for the first wire, Young modulus is going to be 60. What will be the extension of a wire of the same material having 4 times the cross-sectional area and twice the original length? So let the first wire have 60 over the area A times the length L. Extension is 80 millimeters. And for the second wire, Young modulus is going to be, remember it is the same material. For the second wire, force is 60. Original length is twice L. Area is 4 times. So area is going to be 4A times extension, which is going to be X. So we equate these two equations and find what X is. So I'll say 60L over 8A is going to be 60 times 2L over 4AX. So 60 cancels, L cancels, A cancels. And we have, on the left, we have 1 over 8. This one is 1, that is 2. So we have 1 over 8 is equal to 1 over 2x. So which makes x to be 4. Because 2x is equal to 8, so x is going to be 4 millimeters. So our answer is going to be B. Tension. The tension in a spring of natural length L0 is first increased from 0 to T1, causing the length to increase to L1. The tension is then reduced to T2, causing the length to decrease to L2, as shown. Which area of the graph represents the work done by the spring during this reduction? Remember, work done is always with the extension axis. So it should be with the length axis, not the tension. It is extension axis. So extension can be got from the length axis for this particular graph. So any area with the vertical axis is going to be out. We have MLP. MLP, that one is this. Remember, the change in length is L2 and L1. Change in tension is that. So MLP, that is out because it is involving this part of the graph. MNQP. I think this is the correct answer. This is the area that we are talking about. MNQP, that is the area which represents the work done by the spring during this reduction. The graph shown was plotted in an experiment on a metal wire. The shaded area represents the total strain energy stored in stretching the wire. How should the axes be labeled? Okay, so we have force, extension, and so on and so forth. This cannot be stress against strain because we know F is equal to Kx. For the wire, elastic potential energy will be a half Fx, or it can be equal to a half Kx squared, and we can't put K on the end of the axis. So for the answer is strictly going to be A, force against extension. That's how the area gives us the strain energy. It can't be stress against strain because for stress against strain, the area gives us elastic potential energy per unit volume. Nylon breaks when the stress within it reaches 10 power 9 pascals. Which range includes the heaviest load that could be lifted by a nylon thread of diameter 1 millimeter? So stress is equal to force over cross-sectional area, and they have given us diameter, so this becomes 4F over pi d squared, which implies that F is equal to sigma pi d squared divided by 4. So I can find F by simply substituting the values here. So this is 10 power 9, or 1 times 10 power 9 times pi times diameter, which is 1 times 10 power negative 3, divided by 4. So from my calculator, 1 exponent 9 times pi times 1 exponent negative 3 divided by 4. So this is giving me 7. I hope I converted it very, very well. Pi d squared. Sorry, this is squared. So 1 exponent 9 times pi times 1 exponent negative 3, and this is squared, divided by 4. So that is 787.85. So the answer is in the range, it is above 200. So the answer is between 200 and 2000. So the answer is C. A number of similar springs, each having the same spring constant, are joined in 3 arrangements, X, Y, and Z. The same load is applied to each. So since this is the same load, then it is very easy. The extension here is going to be a half E. This is a half E plus a half E. A half E plus a half E, which gives us E. This is a half E plus E, which gives us 3 over 2E. So this is 3 over 2E, this is E, this is a half E. What is the total? What is the order of increasing extension for these arrangements? So X has the smallest and Z has the greatest, so the answer is A. Cylindrical samples of steel, glass, and rubber are each subjected to a gradually increasing tensile force F. The extensions E are measured and graphs are plotted as shown below. Which row correctly relates the graphs to materials? Of course, this might be, because this stretches up to the elastic limit, it might be rubber. Sorry, it might be glass, because here it is only undergoing elastic deformation. Graph Y is showing elastic deformation and then plastic deformation. Graph X harder to stretch initially, then easy to stretch, then harder to stretch. This is automatically rubber. So this is rubber, this could be steel, and this could be glass. So the answer is X is rubber. X is rubber. So the answer is automatically D. Two steel wires P and Q have length L and 2L respectively, and the cross-sectional area A and A over 2 respectively. Both wires obey Hooke's law. What is the ratio tension in P over tension in Q when both wires are stretched to the same extension? So both wires are stretched to the same extension. We know that extension is equal to force over cross-sectional area, then times original length over extension. Sorry, Young modulus is force over area times the original length over extension. So Young modulus is going to be the tension in P divided by two steel wires P and Q have length L. Okay, so tension in P divided by the area, which is for P area is going to be M, then times original length, let it be L, and extension, because they have the same extension, so I'll just say E. Then for Q, hope they're from the same material, they are both steel wires, so Young modulus is the same. E is also going to be tension in Q over the cross-sectional area, which is now A over 2. The original length for Q is twice L, so I'll say 2L. The extension is the same E. So I'm going to equate the two equations. So I'm saying T for P over A, L over E should be equal to TQ times 2L divided by the 2 goes up in the denominator and it becomes 2 and M times E. So AE has cancelled out, L has also cancelled. So note that T in P over T in Q is going to be equal to actually 4 over 1. So our answer is going to be D, because I've multiplied this 2 by the other 2, so I got 4 over 1. In describing the behavior of a spring, the spring constant is used. Different loads are used to extend the spring by different amounts. To find a spring constant, which quantities are required? To find a spring constant, which quantities are required? We know that force is equal to K times X. So it means if I have the load and the extension, I can find K. So the answer is going to be C. The loads and the extensions of the spring, the answer is C. A piece of copper is drawn into a continuous wire. What behavior is the copper exhibiting? Remember I said this is behavior of materials, which is out of the syllabus, but still we can answer this. A piece of copper is drawn into a continuous wire. It means it has undergone elastic and plastic deformation. So what behavior is the copper exhibiting? If it is now drawn into a continuous wire, then it must be showing plastic behavior only. So the answer is going to be C. It would have been both elastic and plastic, but now if it is drawn into a continuous wire, we can't say it is elastic only. No. We can't say it is brittle because brittle it breaks. We can't say it is both brittle and elastic. So the answer is going to be plastic because it is being drawn into different shapes without breaking, so it is showing plastic behavior. The force extension graph of a particular sample of rubber as a load is applied and then removed is shown here. What does the shaded area represent? Now note that the area below the upper curve with the x-axis is the work done in loading. The area below the lower curve with the x-axis is the energy which is recovered when the deforming force has been removed. So let's see the options. The energy transformed into heat during the complete cycle, this would be maybe this part. The recoverable elastic potential energy stored. So the answer is going to be B. This is the energy which can only be recovered at maximum extension. A spring of unstretched length 0.5 meters is stretched by a force of 2 newtons to a new length of 0.9 meters. The variation of its length with tension is shown below. How much strain energy is stored in the spring? So strain energy will be represented by that area. So energy is going to be that area that I've shaded, which is going to be a half times the height, which is 2, then times the base, which is 0.9 minus 0.5, which is 0.4. So this gives us 0.4 joules. So the answer is going to be A. A simple crane consists of a rigid vertical pillar supporting a horizontal beam. A weight W is lifted by a rope at the end of the beam. What are the forces at points X, Y, and Z? To begin with, this beam is actually causing this part is being compressed. This part is under compression, but this part is being pulled apart. Then this part is also being pulled apart because the other bottom is fixed, and it's like this is pulling away. The upper part of the beam is pulling away. So X is under tension, Y is under tension, Z is under compression. So let's see the options. X, we said it is under tension, so compression is out. And we said Z is under compression. So Z is under compression, so A is also out. So the answer is B. A spring cones of length 100 millimeters is compressed by a force. The graph shows the variation of the length L of the spring with the compression force F. What is the energy stored in the spring when the length is 70 millimeters? So length is 70 millimeters, and the force is going to be 6. The force is going to be 6 newtons. So the energy is going to be equal to a half times, of course, it is a half Fx, or it is a half. I'm just finding the area because they said the original length is 100, it is compressed. So I'm going to get the area under this part here. So it is a half times 6, then times, this changes from, it is compressed. So this is going to be 100 minus 70. 100 minus 70, because it is compressed to a compression of a length of 70. That means the load is 6 newtons. So this is 100 minus 70, then times 10 power negative 3. So this gives us, this cancels to gives us 3. And I think this is 30. So I think the answer is 30 times 3, which is 90 times 10 power negative 3. So that is 90 times 10 power negative 3. Okay, so 90 times 10 power negative 3, which gives us 0.09. So the answer is going to be A. The Young modulus of steel is determined using a length of steel wire and is found to have the value E. Another experiment is carried out using a wire of the same steel, but of twice the length and half the diameter. What value is obtained for the Young modulus in the second experiment? So without any explanation, it is the same steel, so the Young modulus is the same, so the answer is automatically C. Four materials are formed into rods of the same dimensions at room temperature, which can sustain the largest plastic deformation. The largest plastic deformation. A ductile material of aluminium, that is not correct. The brittle, of course, is going to easily break. A brittle, those two are out. Now we have aluminium and steel. Of course, steel can sustain the largest plastic deformation without breaking at room temperature compared to aluminium? I say these questions are about materials, which is out of the syllabus, but we can just have a clue about them. So the ductile material steel can sustain the largest plastic deformation compared to a ductile material of aluminium because of the Young Modulus. A rubber band is stretched by hanging weights on it and a force extension graph is plotted. What is the best estimate of the strain energy stored in the rubber band when it is extended 30 centimeters? So we have done this similar question where I said, first of all, I could find the area of the upper rectangle up to this point here. And we said the energy must be less than that area, must be less than 17 on the vertical. Yes, 17 times 30 times 10 power negative 2. So the energy must be less than that value, 17 times 30 exponent negative 2. So the energy must be less than, the elastic potential energy must be less than 5.1. So D and C are wrong. Then I also drew another triangle here inside. I drew a triangle inside here, and I say the elastic potential energy must be greater than the area of this triangle here. So it must be greater than a half times 30 times 10 power negative 2 times, this is 6, 7, 8. So that is times 8. So 0.5 times 30 exponent negative 2 times 8. So it should be greater than 1.2 joules. I hope it is 1.2. No, this is 9. So this is 9. So 0.5 times 30 exponent negative 2 times 9, which is 1.35. And when you check, when you inspect this area here, you notice that is almost half of 1.35. So half of 1.35, it means the elastic potential energy is going to be approximately 1.35 plus approximately half of 1.35. So we can check half of 1.35 is equal to that one, then plus 1.35, which gives us a closest answer as 2.0. So this is approximately 2.0. So the answer is going to be A. The variation of extension X of the spring with applied force F is shown in the diagram here. Which shaded area represents the work done? This is force against extension. Which shaded area represents the work done when the extension is increased from x1 to x2? So this one is wrong, of course, it is including that. This one is also wrong. So we have these two options. But this one is showing, this one is automatically wrong because it's including this area here. So this is wrong. The answer is going to be C because the work done is the area under the graph, not including above the graph. And it's the area with the x-axis. Two springs P and Q both obey Hooke's law. They have spring constants 2K and K respectively. The springs are stretched separately by a force that is gradually increased from 0 up to a certain maximum value. The same for each spring. The work done in stretching spring P is WP. The work done in stretching Q is WQ. How is WP raised to WQ? So first of all, let's find the extensions and the force. For a spring whose constant is K, let its extension be E and the load applied is F. So that means the work done for this spring, which is P, is going to be equal to a half times times F times E. That is the work done for P. Then for a spring whose constant is twice k, the extension is going to be a half e. Remember we said we just look at the coefficient of k and we get the reciprocal to get the total extension. Then the same load is applied F. So it means the work done for this Q is going to be a half, then times F, then times the extension, which is a half E. So it means I have this as a half into, again, a half F times E. But know that a half FE is WP. So it means WQ is going to be the same as a half of WP. So the answer is going to be, which one? Sorry. Two springs P and Q. Oh, so this is P. The first one is Q because P is the one coming first. So this is the first one is Q. The second one is P. So this is P. So this is Q. So WP is a half WQ. So the answer is going to be B. What is the Young modulus of a material that is stress over strain? The answer is automatically D. The graph shows how the extension of a spring varies with the force used to stretch it. What is the strain energy stored in the spring when the extension is 4 centimeters? So strain energy is simply going to be equal to a half times F times X. So this will be a half times X, F is 3,000, it is 30,000, so I will add 1 0, then times X, which is 4 times 10 power negative 2. So 30,000 times 4 exponent negative 2 divided by 2, that is 600 joules. So the answer is going to be C. The table shows a load applied to 4 wires and a cross-sectional area of each. Which of the wires is subject to the greatest stress? So we know that stress is equal to force over area. So just compute the force over cross-sectional area for both. I will not convert the area. I'll just say 1500 divided by 0.25, that is 6,000. Of course, this is 2,000. Then let's say 3,000 divided by 0.56. This is 5,357, around there. Then we have 5,000 divided by 2.3. So this is 2,173. So the answer is going to be A. The force F required to extend a sample of rubber by a distance x is found to vary as shown. The energy stored in the rubber for an extension of 5 meters is, so let's look for 5 meters. So this is 40. So this energy should be less than the area of that rectangle that I've drawn. It should be less than 5 times 400. So it should be less than 2. That means energy should be less than 200. So this is 40. So that gives us 200. So the energy should be less than 200. So this one is wrong. More than 200, that is wrong. Then I'll also draw a triangle inside. I can draw here a triangle. So the energy again should also be less than the area of that triangle, should be less than a half times 5 times 40. So it means the energy should be less than 100 joules. So this one is also wrong. It can't be 100, it should be less than 100. So the answer is going to be A. A wire stretches 80 millimeters and a load of 60 newtons. A second wire of the same material, that means same Young modulus, with half the diameter and a quarter of the original length of the first wire is stretched by the same load. Assuming that Hooke's law is obeyed, what is the extension of this wire? So let's first find the Young modulus. We know that Young modulus is going to be equal to 4f over pi d squared, then times original length over extension. So this is, since it is the same, I'm just going to equate. For the first y, it is going to be 4, f is 60, the length is L, this is pi d squared. I will not change the extension. So this is going to be times 8. So this should also be equal to the second y. This will be 4 times 60. Then times the length is a quarter. So I will say times a quarter of L divided by pi. And the diameter is a half. So this will be a half d squared. Then times the extension, which is not known. So 4 cancels, 60 cancels, L cancels, pi cancels. So I remain with 1 over d squared times 8 being equal to a quarter. The 4 goes up, down. So it will be 1 over 4. There's the 2 in the denominator, which, okay, a quarter divided by 1 over 4 d squared times x. So the a quarter has also cancelled. So you have d squared has also cancelled. It means we have that 1 over 8 is equal to 1 over x. So it means x is still 8 millimeters. What is represented by the gradient of a graph of force against extension? I think that is spring constant. F is equal to kx. What is the unit of the Young modulus? We know Young modulus is going to be, it is Newton, because it's stress, which is force. Stress over strain. Strain has no units. Stress is force over area times original length over extension. So this is Newtons over meters squared times meters over meters. So this one cancels, so it is Newtons per meter squared. What is plastic deformation? Of course, plastic deformation, there's the options which are there. When a material undergoes plastic deformation, even if we remove the deforming force, the material does not return to its original length. So plastic deformation occurs when strain is not proportional to stress, but when the load is removed, the material returns. It does not. Plastic deformation occurs if, when the load is removed, the material contracts, but a permanent stretching has occurred. So the answer is going to be B. The material has retained it retains some extension. So a permanent stretching has occurred. The graph shows how the length of a particular rubber cord varies as force is applied. What is the maximum strain energy in this deformed rubber? So energy is going to be the area with the extension axis, which is now on the length axis. So energy is going to be a half Fx, which is a half, and F is 25. X is 0.4 minus 0.2, which is 0.2. So I think the answer here is going to be 2.5, because 25 times 0.2 is 5. Then divide by 2, it is 2.5. So the answer is going to be A. Which properties best describe modeling clay? Modeling clay, of course, does not just it can be modeled into any shape. But when when you remove the deforming force, it remains in its new shape. So we can't say it is elastic. It does not just break. So it is plastic. It can show plastic, and it can be molded because it's modeling. It can be molded in any shape. So it is plastic and ductile. A number of similar springs, each having the same spring constant, are joined in 4 arrangements. The same load is added. Which arrangement gives the greatest extension? So here we just check. A is having extension, which is a half E plus a half E, which is E, a half E plus E, which is 3 over 2E. This is a third E plus E. Where is it a third? There are 3 springs. That's why I'm saying it is a third. Here I said it is a half E plus a half E, which is E. So a third E plus E, which gives us what is a third E plus E, a third E plus E. LCM is 3. So we have E plus 3E, that gives us 4E over 3. So which one is greater? 4E over 3 and then 3E over 2. Let's compare those two. 3 divided by 2 is 1.5. Then 4 divided by 3 is 1.3. So the answer is going to be C. The graphs show how force varies with extension and stress varies with strain for the loading of a metal wire. The Young modulus for this wire is equal to the gradient of course, Young modulus is going to be the gradient of the stress against strain curve. This one is wrong. The area between the force extension graph and the extension, that is elastic potential energy, the gradient of stress strain graph. So the answer is C. For a wire, Hooke's law is obeyed for a tension F and extension X. The Young modulus for the material of the wire is E. Which expression represents the elastic strain energy stored in the wire? Force against extension. The Young modulus for the material is E. So we know E, Young modulus is equal to the stress, which is force over area. Which expression represents the elastic strain energy? Energy is equal to simply a half kx squared or a half fx. So energy, elastic potential energy, so I don't need the Young modulus. Elastic potential energy is a half fx, so the answer is automatically C. Two trolleys are placed together on a horizontal runway with a compressed spring between them. When they are released, the 2 kg trolley moves to the left. So this one moves to the left with a speed of 2 meters per second, which means this should also move to the right to conserve momentum. So by conservation of momentum, if they are initially released, it means initial momentum was 0. So let the speed of this one be v. So after release, the momentum must be conserved. So we shall say momentum to the left is maybe negative, momentum to the right is positive. So momentum to the right will be the mass, which is 1 kg, because momentum is mass times velocity. So 1 kg times the velocity v. Then momentum to the right is negative, let's say minus 2 times 2. So I just wanted to get v as, when I make v the subject, v is going to be 3 meters per second. So the 1 kg moves with the 3 meters per second to the right hand side. How much energy was stored in the spring? So the elastic potential energy is going to be equal to the total kinetic energy after release, which is going to be a half for the first one, which is going to be times 2 squared, plus for the other one, which is also a half. By the way, this is a half mv squared. For the other mass of 1 kg to be a half times 1 times 3 squared, the total kinetic energy after release. So this one is going to be 4 plus 9 over 2, which is it 9? Sorry, this was 4 meters per second, because this is 1 times v. When it crosses, is 4 meters per second. So this is 4 squared. That is 4 squared. And 4 squared is 16 divided by 2, that is 8, which gives us 12 joules. So our answer is going to be D. Which role best defines elastic and plastic behavior of a material? Elastic, we know that when the load is removed, the material returns to its original length or its original shape or size. So extends only when within the limit of proportionality, not at all. Has a linear force extension curve. Okay, that is true, but obeys Hooke's law, that is true. returns original shape and size. That is true. Okay, let's check the plastic. Extends beyond the limit of proportionality, which is true, but we have already eliminated A. Has a horizontal force extension curve. Has a horizontal force extension curve. Okay, has a linear force extension curve. Rubber does not have a linear force extension curve, but it shows elastic behavior. So this one is also out. So B is out. Obeys Hooke's law. Rubber does not obey Hooke's law, but still has an elastic behavior. So this one is out. So this means our answer is going to be D. Returns to its original shape and size and suffers permanent deformation. Last but not least, a steel string on an electric guitar has the following properties. Diameter is that Young modulus, tension. The string snaps, in other words, breaks and contracts elastically. By what percentage does a length L of a piece of the string contract? So we want the strain, because strain is the extension of original length. That is giving us the percentage by which the length contracts. So Young modulus is equal to stress divided by strain. Young modulus is stress divided by strain. So the strain is going to be equal to the stress over Young modulus. So this will be equal to force over area times the Young modulus, which is area is pi. Remember, area is pi d squared over 4. So this becomes 4f divided by pi d squared times E. So this becomes 4 times the force, which is 20, divided by pi, diameter is 5 times 10 power negative 2 squared. Then the Young modulus is 2 times 10 power 11. So this is going to give us, I'll just multiply it by 100 to change it to percentage. So this is a 4 times 20 divided by 2 exponent 11 divided by pi times, or pi into brackets 5 exponent negative 2, but this is squared. So I'm getting 2.05. Let me check it again. 4 times 20 divided by, open brackets, pi times, sorry, this is negative 4, divided by pi exponent negative 4, but it is squared, divided by 2 exponent 11. Okay, that is 5.1. 5.1 times 10 power negative 4. Remember, strain is extension of original length, so it is a ratio of the change in length. So this is going to be equal to 5.1 times 10 power negative 4 times 100 to change it to percentage, which is 5.1 times 10 power negative 2%. So the answer is going to be B. Okay, that marks the end of deformation of solids. My pen has stopped working. I may take some time to receive a new battery for my pen because it is hard to find. Nevertheless, I'll try my level best. Have a blessed day. Bye bye.